So next up is I want to show you an example of a problem where Newton's third law is a crucial part of how you solve it. So this is a problem I have in my lecture notes. We have here a sled with a stack of boxes on top of it. And then the sled gets pulled by a dog and the boxes don't fall off the sled. So what's the acceleration of all these things and what friction forces are going to be required to hold those boxes in place? So in other words, I have a setup that's kind of like this. I have things stacked on top of each other, and you pull on the bottom one in the stack and the top one doesn't fall off. So I'm not actually exerting a force on this block, right? So why doesn't it fall off if there's no force on it? And the answer is because the box on the bottom has to exert a force on this box to hold it in place. So there's interactions between these two objects that are keeping the motion in place. So let's solve it. Okay. Step one. Now I'm going to start out with the Newton's second law framework here. Newton's third law will come into play for how we list off the different forces that are involved. But we're in the overall Newton's second law framework for how to solve it. So the first thing I need to do is step one, draw a free body diagram for every single object in the problem. Okay, so first of all, we've got the sled. Okay, so here's the sled. Let's put it like that. Second of all, then we have the dog. I actually don't need to draw the diagram for the dog. You can draw it if you want to, but it's not going to matter. Next, I have a 25 kilogram box that's sitting on the sled. So I'll put that like here. Now, just as a little tip, for free body diagrams, you don't want to put them too close together just because it starts to get really cluttered and confusing. So I'm going to put a little gap between them so that I can make sure I can see what's going on, even though they're actually touching each other. And then on top of that, I have another box. So like here, let's say. Okay, and again, I'll space it out a little bit. And let me make note of the masses so that I can just help myself keep track of everything. So this is the 50 kilogram sled. And this one here is the 25 kilogram box. And this one here is a 10 kilogram box. Okay. Now, next thing we do is we start listing off what are the forces here. I'm only going to bother with the horizontal forces, partly just to make this a little bit cleaner, and partly because I haven't talked about gravity or anything like that yet. So we don't actually know much about the vertical forces, and I don't want to get sidetracked having to introduce a bunch of other stuff. So I'm only going to draw the horizontal forces. And remember, F equals ma is decoupled in the sense that the horizontal direction and the vertical direction can be solved separately. So it's fine to do that because as long as I include all the forces that have horizontal components, I can still solve the horizontal part of the problem. Anyway, so what are the horizontal forces acting on the system here? The first and most obvious one is, it says in the question that the dog is pulling on the sled. The bottom one is the sled here. So let's say the dog is pulling it in this direction. And that force, let me label them all using the same system. The system I mentioned in the last video. This is the force of the dog on the sled. So I'll make it FDS. And this here, this is going to be the sled. I'll call this box A, and I'll call this box B for labeling purposes. Okay, so the dog pulls the sled forward. Notice the dog is not pulling the boxes forward. It says he's pulling the sled forward. The dog pulling is not directly what is causing the boxes to move, only indirectly. So we do not include the force of the dog pulling the boxes forward because he isn't pulling the boxes forward. So that's the only force that's directly given in the question. So now we have to ask ourselves, well, what are the other forces here? what are the forces that are causing the boxes to move. So if you think about it for a minute, you can probably convince yourself, like I was saying, that if I pull the bottom box forward, the reason the top box moves is because there's a force of the bottom box acting on the top box. So the bottom box is actually pulling the top box forward through this contact that they have where they're sitting on top of each other. Another way to convince yourself of this, imagine that I lubricated this surface here and made it extremely slippery, and then I pulled this box. What would happen is it wouldn't take this one with it, and this one would fall off the back, which can happen if you have a bunch of stuff stacked up on like a cart and you pull the cart too fast, everything falls off the back. That's because the force provided by the cart on those boxes was not sufficient to pull them forward as fast as you wanted them to accelerate. But anyway, I digress. If you can convince yourself of that, then you can convince yourself there must be a force pulling this one forward, and there must be a force pulling this one forward. So the reason why box A is getting pulled forward is because it's getting pulled forward by the sled. So you're going to have a force of the sled on box A. And by exactly the same logic, the reason why box B is moving forward is because box A is pulling box B forward. Okay? Now, here's where Newton's third law comes into play. I put a force here, FSA, the force of the sled on A. If the sled is exerting a force on A, Newton's third law says that A also has to be exerting a force on the sled. So I have to include that force as well. The force, so first of all, FSA is in diagram A. The third law pair for that, FAS, will be in diagram S. So now I'm turning my attention to diagram S, and I know that the direction of that force has to be opposite of FSA. So that means this way. So there's going to be a backwards force like that. This is going to be FA on S. Box A acting on the sled, pulling it backwards. So this force, what does this force feel like? Is, if say you had a bunch of stuff stacked up on your back and you tried to accelerate forward, you would feel that load holding you back. That's basically that force. You have to exert a force on that load to pull it with you. And so by Newton's third law, you feel that load pulling you backwards. So the box is pulling the sled backwards. The sled is pulling the load forwards. And then by exactly the same logic, I also need to include a third law pair for FAB. So the third law pair for FAB is going to be FBA, which should be in A's free body diagram. So that's going to be here. Again, backwards because I know it has to be opposite of the one I already drew. So this is FBA. Okay. FDS does not need a third law pair here. The reason why is, although every force in the universe has a third law pair, that doesn't necessarily mean that you actually care about the third law pair all the time. In this case, that's the force of the dog on the sled. So the third law pair for that would be the force of the sled on the dog. So that force would go into the dog's free body diagram, but I'm not drawing the dog's free body diagram, so I don't really care. That's just the force that the dog feels pulling him backwards when he tries to pull the sled forwards, which is irrelevant so far for this problem, unless the question asks me something about the dog. So as a result, I think I'm done. I think those are the only forces I need. I've got a force, a reason why every block is accelerating forwards, and I've got third law pairs for all the ones that involve interactions between two of the diagrams. And by the way, I don't have an interaction between B and S because those ones aren't touching directly, so they're not directly exerting forces on each other. Only A and B are touching, and S and A are touching, so those ones have third law pairs. Okay. Anyways, free body diagram's done. As I've said in some previous videos, that was actually the hard part. The rest is just applying the procedure. Next thing I need to do is, the next thing I would normally do is break forces into components. I don't need to do that here because everything is already just in the X direction, so there's no components to calculate. The next thing I need to do is sum the forces and then set it equal to MA. Now, since I have 3 diagrams, I have to do that separately for every diagram. So for diagram B, there's only one force in the diagram. It's in the positive direction. So it's just going to be FAB equals, I'm solving diagram B, which has a mass of 10 kilograms. So I'll have 10. You know what? I'm going to drop all the units just to save myself from having to write kilogram 100,000 times and clutter up the slide here. So I'm just going to say 10A. For diagram A, that has 2 forces in the diagram, so those need to be summed. And although I don't have to break things into components, the components do still have positive and negative sign. So I do have to include the sign. So this one's going to be FSA minus FBA equals 25A. And it's the same A in this case because the boxes are all moving together as a unit, so they all have the same acceleration. Normally you would have a separate acceleration if they're not accelerating at the same rate. Okay. And then anyways, the sled down here, the equation for that is going to be FDS minus FAS equals 50A. Okay. And now I've got 3 equations. Next thing I should check is how many unknowns do I have? Because if I have 3 equations, I'm expecting 3 unknowns if this is a solvable problem. Okay, so what are my knowns and my unknowns here? I know FDS, that was given in the question. So let me plug that in. That was given as here, 100 Newton. And I'll drop the units again. So I'm gonna just make that 100. The other thing that you have to realize with Newton's third law is Newton's third law pairs are equal and opposite, not just opposite, but equal and opposite. So that means FAS is actually equal to FSA because those are just the magnitudes of the vector, those variables. So as a result, the magnitudes are the same. So I can just erase one of these and replace it because it's not going to change anything because I want to reduce the number of variables in my equation here. And same thing here. Let me get rid of BA there and replace it with AB. Okay, now I'm down to 3 variables. So my 3 variables are FAB, FSA, and A. So that's 3 variables, 3 equations. I'm in business. This is a solvable problem. So now I just have to do the algebra. Now I just have to solve this as a system of 3 equations with 3 unknowns. So the rest is just a math problem now. Let me go ahead and do it for those who want to see it. I think easiest way to solve this one, the first equation here, the top equation, is already solved for FAB. So let's plug this in. So I'm just going to take this 10A and plug in here. And that will give me, I'll be down to 2 equations. So I'll have FSA minus 10A equals 25A. So that tells me FSA equals 35A. Okay. And then just get rid of all these arrows cluttering things up. Now I'm going to take this result here and plug into there. So then I'll have 100 minus 35A equals 50A. So that gives me 100 equals 85A, which means A equals 100 divide 85 is 1.18 meters per square second. So there's the first question answered. What is the acceleration? That's done. The other question is, what are the friction forces at the contact surfaces? That means it's looking for FAB and FSA. So I now take this result that I got for the acceleration, plug in here, and also plug in here to get the other two quantities. So I'm going to have FSA equals 35 times 1.18, and that will give me 41.2 newtons, and FAB is 10A, so that's 10 times 1.18, and that will be 11.8 newtons. So there is the second part of the answer of the two contact forces. Okay, so notice I used just the same F equals ma procedure that I said earlier would be like the main foundation we keep coming back to, and I mixed that together with some of what we learned in the Newton's third law lecture of how to handle third law pairs and multiple free body diagram problems.